So welcome to all of you here in the lecture theatre tonight, and obviously welcome to those of you who are watching online. Great pleasure to introduce Professor Nick Wright to you tonight to give his inaugural lecture. But I'd like to say also a very special welcome to Nick's family who are supporting him tonight, along with his colleagues here at Keele, and I'm sure other friends too. Special thanks and warm welcome to his wife Elizabeth, his 4 children, Edward, Anne, Penelope and Dylan, who I'm reliably told are the best behaved children in the whole lecture theatre. That's what I've been told tonight. Also, a very warm welcome to Nick's parents, Mum Christine, Dad Tony and their partners, and also to Nick's godfather, David, and his wife. Thank you so much for coming to support. An inaugural lecture is a very, very special occasion. And it's really just such a memorable occasion for any professor. So I'm sure we'll all enjoy Nick's talk tonight. So over to our star turn tonight, Nick. Nick is Professor of Astrophysics in the School of Chemical and Physical Sciences and Director of the Astrophysics Research Centre here at Keele. Nick completed his PhD in astrophysics at University College London in 2009 before moving to the Harvard-Smithsonian Centre for Astrophysics as a postdoctoral fellow. He was awarded a Royal Astronomical Society Fellowship in 2012 and an Ernest Rutherford Fellowship in 2015, which he brought here to Keele, and we were very glad to welcome him here in 2015. He was awarded a lectureship in 2020 and a chair in astrophysics in 2025. So in his inaugural lecture tonight, Nick is going to share his career in astrophysics and his work studying the motions of stars to understand the formation and dissolution of star clusters. Nick, welcome.
Hi everyone. Right, thank you all for coming. I'm very honoured and very happy to be stood here in front of you. And it turns out that, like most people who find themselves delivering an inaugural lecture, the first thing you do is you go and watch as many inaugural lectures as you can online, and fortunately Keele has many online, to try to understand what an inaugural lecture is, because I couldn't say I really had a thorough view of what one was. And I think the best description of one I had was, I think, in Alex Lamont's inaugural lecture, where she described it as a chance for your friends and family to understand what you do at work and your work colleagues to understand what you do at home. So I'm going to try to do that. I'm not going to make it very heavy on the science, because I think those of you who work with me don't want to hear it again, and those of you who don't work with me would probably rather hear about something else. So I'm going to try to talk about my life that's gotten me to here, and a little bit about some background into the science and what I do and what excites me. Right, I'm going to start with this picture. I'm the one in the middle. This is me and my sisters, Jenny and Elena. They've been labelled so you can tell them apart, because they are identical twins. And in pictures like this, sometimes it's only me and my mum that can tell them apart. This is taken, I think, when I'm about 6 or 7. And this would have been taken probably in Abingdon in Oxfordshire, where I spent the first 7 years of my life, before we moved to Hampshire, between Winchester and Southampton, where I spent the rest of my childhood. And I had a pretty amazing childhood, I have to say. It was full of love and happiness and trips out on steam trains and to parks, and to see grandparents. This is in my grandparents' garden in Harrogate. And just an absolutely fantastic childhood, where I've really felt loved and supported. Not a childhood with a huge amount of astronomy in it, I have to say. Certainly growing up in the 1980s and 1990s, there wasn't a huge amount of astronomy in the curriculum, so I wasn't exposed to it much in the classroom, but fortunately my grandfather introduced astronomy to me. This is my grandfather, Kenneth Clark. He was in the Royal Navy during the Second World War, on ships and then as a submarine commander, and he knew the night sky very well, and so he would take me out in the evening and show me the night sky. And I can't confess to have remembered everything he taught me, but it did begin to kindle a fascination in the night sky. That took a big upturn in the 1990s when we began to get images back from some of the missions to the outer planets. The Voyager 2 mission visited Neptune and Uranus and sent back these gorgeous color images of these planets here that had previously been limited to much lower resolution black and white images. And then in the mid-90s, the Galileo mission went to Jupiter and Jupiter's moons and sent back some absolutely stunning images. And these would filter through the news media into books and TV shows, and I absolutely love these. I have a memory of me sitting in the bath at age sort of 12 or 13 looking at books with these pictures in them. And it really not only began to inspire me in astronomy, but also from this sort of artistic beauty that comes from space and the night sky. I went to study at the University of Bristol in 1999. I actually went to do a degree in physics with maths. And then on the first day, I was handed out my timetable, and I found out that the physics part of the degree was 50% maths anyway. And I thought there was absolutely no chance I was going to spend 4 years with 3/4 of my time dedicated to maths. Apologies to any mathematicians in the room. So I looked at what else they offered, and I saw there was the option to study physics with astrophysics. So on a kind of whim, I switched. And I spent 4 wonderful years studying physics with astrophysics at Bristol. And unlike astronomy and astrophysics at secondary school or at high school, at university, the richness of the physical understanding that goes behind astrophysics was a lot more interesting and appealing to me. I was very fortunate that after my second year of undergraduate study, I was invited to attend an undergraduate summer school at the University of Cambridge. This is me with my dad punting down the River Cam. This was all expenses paid summer at the University of Cambridge, where we had lectures from staff at the university, and also got to take part in a research project. This is Stephen Smart, who I worked with on a project for a month or so. And we studied this star cluster here, NGC 3603. This is one of the most massive star clusters in our galaxy. There are 20 to 30,000 stars that have recently been born in this cluster. And within the cluster as well, there's a number of really, really massive stars with masses or tens or maybe even 100 times that of the sun. And we studied this object here. It's called Share 25, which in astronomy language means it's the 25th object in a catalogue by Share. And this is what's called a blue supergiant, a very, very hot and very, very luminous type of star. But this is a star that also seems to have ejected some material. There's a lobe of material out here, there's something here, and there's possibly a disk of material. And that's not behavior that we normally see in blue supergiants. That's something we normally see in red supergiants, which are slightly cooler but luminous stars. And so there was some understanding at the time as to whether blue supergiants evolved into red supergiants or vice versa. And this seemed to be an object that had gone from being a red supergiant to a blue supergiant, which was quite unusual. Anyway, I got to the end of my undergraduate studies, and I had to do a final year project in astrophysics, or a final year project in any subject I wanted. And I was given the option of a huge array of astrophysics projects from the astrophysics group at Bristol. But I thought to myself, I kind of know I like astrophysics. I know I'd love to do a career in astrophysics. And so I thought to myself, I'm not going to take a final year project in astrophysics. I'm going to explore one of my other loves, which if you know me, my main other love is in food and drink. And the project was available to work with Professor Peter Barham to do a collaborative project with this man here, Heston Blumenthal, who had at the time just recently been awarded his first Michelin star at the Fat Duck restaurant. And I spent a year working with these two people, designing and working on the food of science. We would work together to think about dishes, do scientific projects to help him improve his cooking process, and it was an absolutely fantastic year. Our main project was to try and take a liquid that had a certain color and a certain aroma, say, for example, a chicken stock, and do our best to remove as much of the color as possible while keeping the aroma, so that when it was put in front of somebody, nobody had any preconceived ideas about what the food was. That was something that Heston was really interested in, how when we take a bite out of something, we already pretty much know what it tastes like. If I put a strawberry in front of you, you all already know what a strawberry tastes like, and our brains have already done a lot of the hard work. And he wanted to remove that and see if he could surprise people. So we designed a machine and we made quantitative measurements of the opacity of the liquid and the aromas of it, and we were able to remove a lot of the color and opacity from a liquid while retaining its flavor. So that was great fun. And I got to eat at a Michelin star restaurant multiple times for free, which was really good as a student. Peter was also really, really supportive of me exploring other aspects of the science of cooking. He had a little party trick whereby he would take a lecture hall full of students and a bowl full of cream and pour liquid nitrogen on it to make instant ice cream. And he encouraged me to try this project. He lent me a dewar full of liquid nitrogen. I'm glad Graham isn't here tonight because this would definitely not pass health and safety these days. And he let me take it home to my flat in Bristol where my family, my mum, my sister, and my auntie were visiting. And in front of them, we made liquid nitrogen instantaneous ice cream. And he was really, really supportive of that sort of exploring the magic of science, if you will. Following my degree, I went traveling for a year, and I was then very fortunate to be offered a place to study at University College London for my PhD, to work with Professor Mike Barlow. Mike is one of the kindest and most intelligent people I have ever met. And this wasn't a view just held by me. When I went to his retirement party a few years ago, every single person shared exactly the same view of him. Mike would always be so forthcoming with any knowledge that he had on any subject, and not in a sort of selfish way to sort of let you know that he knew a lot. He just wanted to share and help. And he was a wonderful PhD supervisor. Had an absolutely wonderful 4 years working with him. We spent most of our time studying this object. This is a planetary nebula. It's called NGC 6302. This is a type of star similar to our sun that has reached the end of its life. And as stars like our sun get to the end of their life, they start to shed some of their outer layers. Some of the outer parts of their atmosphere start to drift off into space. That's this material here. And then the inner core of the star gets exposed, and that inner core of the star is quite hot, and it's very luminous, and it begins to illuminate that material and eventually ionize it, stripping its electrons off. And this nebula glows, and you can see these things in distant galaxies. They're so bright. And it's a wonderful way to expose the inner parts of a star while seeing the final stages of stellar evolution play out in front of you. And this was a particularly enigmatic object because it was a lot more energetic than most other planetary nebulae. And we built a three-dimensional model of this, and we're able to confirm that the star in the middle, which you can't actually see because it's obscured by this disk of material, was one of the hottest stars that has ever been discovered. It's got a surface temperature of 220,000 Kelvin, which is much higher than any normal star. I was also very fortunate during my PhD to go to a number of conferences. This is my first conference. I can't actually find myself in this picture, but I haven't looked too hard, I have to admit. I'm probably somewhere at the back. This was in Hawaii. 18 months into my PhD, my supervisor took me to Hawaii. We had a wonderful time. And I really enjoyed conferences as a chance to meet people from different parts of the world, all with a shared interest in science and share our scientific discoveries. I was also very fortunate I got to go observing quite a lot. My supervisor was involved in this survey called IFAS, which was an imaging survey of our Milky Way galaxy, which used not only what are called broadband filters, but also a narrowband filter that isolated ionized hydrogen and produced some really evocative images. This took place on the Isaac Newton telescope, which is perched here. This is the Isaac Newton telescope, 2.5 kilometers up on the island of La Palma, just on the edge of this huge precipice here that plummets down into an extinct volcano down here. And I went for about a week's worth of observing every year during my PhD, and I absolutely loved it. I loved these mountainous, colossal machines that you would poke out into space and resolve beautiful structures in the inky blackness of space, while also being on this rugged landscape and potentially being alone in this giant building for the night, or maybe just with a colleague or something like that. And I really enjoyed observing. As part of that, we also got to get some really beautiful images of space. And my supervisor asked me if I could put these together because he knew I had some Photoshop skills. And we combined images at different filters to produce these 3-color images. This is a star-forming region called the Elephant Trunk Nebula. And we produced lots of these. And they've made their way into newspapers. And they're dotted around universities around the country, which is always a joy when I'm in a university and I find one of these on the wall somewhere. And my mum reminded me a couple of days ago that they were also on display in the Royal Albert Hall for a short period of time. And that was a lovely thing to revisit that artistic side of space that had enthused me. I passed my PhD Viva. This is me with Mike and my friend Antonio. And at that point, I didn't really know what I wanted to do other than to stay in astrophysics. And an opportunity came up to go to Harvard University, to the Harvard-Smithsonian Centre for Astrophysics, and work with Jeremy Drake there. Jeremy was a wonderful person to work with. I initially went for 8 months, but stayed for 5 years, which tells you something about how much I enjoyed myself there. And Jeremy really taught me the importance and the power of being able to make a convincing argument as to why your science should be done. He taught me how to write a good proposal, be it an observing proposal or a funding proposal, where you really have to make it very, very clear why yours is the most important science that has to be done that day. And Jeremy was an expert at that, and I really enjoyed learning that from him. We studied this part of space here. This is the Cygnus OB2 Association, which is one of the regions in space I've studied the most over my career. This is, again, a really, really massive group of stars, similar to that cluster we looked at earlier, with about the same number of stars. But instead of being centrally concentrated like a star cluster with a nice round morphology, it's a lot more spread out. And this wasn't really known at the time why this was. Why would we get groups of young stars that were round and concentrated and others that were more spread out? And that was something we worked on. We had data from NASA's Chandra X-ray Observatory. We had a little bit of data, and we analyzed it, and then we wrote to NASA and said, can we have some more? And they gave us 2 weeks of time on the observatory. It was an absolutely huge amount, and we conducted this huge survey of the association, which led to many, many papers, and my PhD student, Joe, is continuing to work on some of that data in different forms. And that was really, really enjoyable. Again, I got to do more observing. I got to go out to the Multiple Mirror Telescope in Arizona. This is an amazing 6.5-meter diameter telescope perched on top of this mountain just south of Tucson, within inside of the Mexican border. It's a couple of kilometers up above the desert floor, again in this beautiful, almost alien landscape where there's snowy mountains leading down to this hot desert floor. And again, just a lovely experience visiting this wild landscape and using this equipment there. I had a fantastic time, that's me there, at the Centre for Astrophysics. It's one of the largest astrophysics research centres in the world. There's about 500 professional astronomers there. And I loved the fact that it was so large and there were so many people there that you could talk to. So many people with different interests, with different scientific histories. And so many people would come visit. You know, we had Nobel Prize winners come to give seminars. We had TV celebrities like Neil deGrasse Tyson, and they would come and they would talk to us, and we had an absolutely fantastic time. And I think one thing I've always encouraged my students and postdocs is if you ever get a chance to go work at one of the largest, research centers in your field, just take it, because it's a wonderful experience being in such a rich environment such as that. As you can probably tell from the fact I spent 5 years there, I really loved Boston. Boston has this wonderful balance between a sort of European historical city with narrow cobbled streets and a big, American city with big tall glass buildings. There's beautiful countryside in the area and a rich sporting history, and I just had an absolutely wonderful 5 years. But I would be amiss if I didn't say that my favorite bit was the food. Because there's food in America that we do not get here, and I mean really good food. There's not only the seafood of the Northeast, which is just so rich and varied. There's American barbecue food, which is completely unlike anything we would be familiar with as barbecue food. But there's also Mexican food, which is obviously not from America, but it has spread into America, and they've changed it. It is not the same as real Mexican food, but it's not food we're familiar with in the UK. I mean, most of us probably couldn't even tell us where the nearest Mexican restaurant is from here. So I'm pretty definite there wasn't one in Stoke the last time I checked, but there might, maybe I'm wrong about that. But discovering Mexican food was an absolute joy. I got to the end of my time at CFA, and I was applying for fellowships, and I got a lot of help from many of my colleagues there, and I was very fortunate to be offered a Royal Astronomical Society Research Fellowship, which I took to the University of Hertfordshire in 2012 to work with Janet Drew. And I'm going to talk a little bit more about the research I did with Janet later. But Janet was a wonderful person to work with at this time in my career because she really instilled in me the importance of being critical of my own ideas. I think all scientists are very good at being critical of other people's ideas. We do that when we referee papers or referee funding proposals. But she really encouraged me that before I put anything out into the community, I should be critical of it. I should criticize my own ideas as if I'm criticizing somebody else's, so that I've really given them the best test they can have before they go out there. I had 3 wonderful years there, and then I again applied for fellowships, and I got offered an STFC Ernest Rutherford Fellowship to come work with Rob at Keele. And I've been at Keele ever since, and I've had a fantastic time with Rob. Rob has taught me about the real value in getting involved in big projects, years or even decades before they see fruition. Shortly after I came to Keele, Rob started to get me involved in some big surveys that were really just at the ideas stage, and some of those are only just coming to fruition now. But because of that investment of time that we've had in them, you know, we're the national experts in using that data for our science, and that's really, really effective when you're trying to make a mark in a certain area. So that was really good. Again, more observing trips, this time to Australia with my first PhD student, Joe, swapping deserts and extinct volcanoes for eucalyptus trees and kangaroos bouncing past the observatory. More snakes, unfortunately, but still a lovely place again to visit. And my time at Keele has been wonderfully rich and full of lovely friends, as I can see you all here. I was very fortunate to meet my wife, Elizabeth, and we got married a few years ago. I'm very happy to say that there are quite a few people in this picture who came from Keele. I can see Jacko and Joanna there, but who are also here today, both friends and family. And I'm also very honored that through my wife, I had 4 wonderful children, Edward, Anne, Penelope, and Dylan, who are all here, I think, and mostly still awake. So I gave the title of this talk, And Yet It Moves, which is a bit self-indulgent, I know. It references the motions of the stars, which is the area that I've mostly worked in. But it also references back to this man, Galileo. Galileo worked 400 years ago at a time when there were major changes going on in our view of astronomy and of the universe. The existing theory at the time for what the sort of universe looked like was that the Earth was stationary and at the center of the universe, and it was surrounded by the known planets, the sun, the moon, and then the distant background stars. And this was the view that Ptolemy had put forward and that the Catholic Church had adopted. And it was the standard view at that time amongst certainly a large chunk of science. But a new model had been put forward a few years earlier by Copernicus, in which instead of the Earth being the center, the sun was the center, and the Earth moved around the sun. And this was an alien concept to many people, because most people couldn't imagine the Earth moving. When you're stood on the Earth, you can't feel that movement. You're stationary. How on earth do you know that the Earth is moving? And yet that was the model that Copernicus was putting forward, and that all the planets orbited the sun. Now, one of Galileo's greatest contributions to astronomy was that he invented the telescope. And one of the first things that he looked at with the telescope was Jupiter, which is shown here. This was in the early days of 1610. I think you can see the day of the month listed down here. And he's showing Jupiter and 4 bright objects that he's observed in the vicinity of Jupiter. And he observes these night after night, and he sees these objects move back and forth around Jupiter. What he's observed there is the moons of Jupiter, the 4 brightest moons of Jupiter that we now know of and call the Galilean moons, but had previously never been known of before. And he correctly concluded that these objects were in orbit around Jupiter, something we now know, of course, to be true. But this was radical at the time, because at that point in time, no object was known that you could definitively say orbited anything else other than, at least from our appearances, the Earth. And so putting forward this idea risked a huge change to the scientific status quo. Later that year, he observed Venus, and he observed the phases that Venus has, similar to the moon. And he observed that the phases of Venus were much more consistent with the idea that Venus was orbiting the sun, rather than if Venus was orbiting the Earth. You can see the phases are very different between those 2 predictions. But again, he was favoring the heliocentric model, whereby everything orbits the sun. 20 years later, Galileo put those ideas forward in the form of a book. This is his dialogue concerning the 2 chief world systems, published in 1632 in Italian. And in this book, he doesn't say what he thinks is the case. He lays out a dialogue, a debate, between 2 individuals who are trying to convince a third person. One of these individuals is called Salviati, and he's supporting the heliocentric model, the modern model, the Copernicus model, that everything goes around the sun. And he's arguing against somebody who is advocating for the Ptolemaic geocentric model. And he called that person Simplicico, which I think is a bit of an indication as to what he thought. And this book went out, and it drew a lot of attention quite quickly, particularly from the Catholic Church, who saw straight through the naming of the characters. And the following year, he was invited in front of the Holy Office. This is a painting from the 19th century showing Galileo being interrogated in front of the Holy Office. And he was, it was suggested that he was holding the false doctrine that the sun was at the center of the world. And he defended himself and said, no, I'm merely presenting this as a hypothesis. I'm presenting all the different views and allowing the reader to look at the evidence and think about which of these models best fits the evidence. They saw straight through that, and they made him a suspect of heresy and condemned him to imprisonment for the rest of his life. The following day, that was reduced to house arrest for the rest of his life, where he spent the rest of his life under house arrest. But it is said, and it's most likely apocryphal, that as he left the courtroom, Galileo uttered the words, "and yet it moves," meaning the Earth moves. The Earth is in orbit around the sun, and that's where those words come from. I wanted to highlight this because it shows the importance of seeing changes in the night sky, because for hundreds of years, people have observed the night sky, the positions of the stars, their brightnesses, and we don't really observe much change. It's very difficult with the naked eye to see a huge amount change in the night sky. And yet, there are lots of things changing. And as astronomy developed, we began to see more and more things that were changing. My interest has been on the motions of stars, in particular what's called the proper motion, which is the movement of stars across the plane of the sky. This is the star with the highest proper motion. It's called Barnard's star. It's the fourth closest star to the sun. And as you can see, over the course of 20 years, it's moving relatively fast relative to at least these other stars here. It's moving at a speed of about 10 arc seconds per year. Now, an arc second is a 60th of an arc minute, and an arc minute is a 60th of a degree. And there are 360 degrees in a circle. So 10 arc seconds per year is not particularly high. In fact, it would take Barnard's star about 180 years to move the width of the full moon. And that would be even harder to observe, given that the Barnard star isn't even visible to the naked eye. It's a 9th magnitude star, and so you'd need a telescope or binoculars to see it. So movements like this were not visible to ancient astronomers. The first star that was observed with a measured proper motion was Arcturus. Now, Arcturus is very bright. It's one of the brightest stars in the sky. If, like me, a week ago, on the hottest day of the year, you were sat outside at 10 p.m. enjoying the warm, sunny weather, and you looked up, the bright star above you would have been Arcturus. And in 1738, the astronomer Cassini compared his measurements of the position of Arcturus with those of astronomers that had come before him, particularly those of Tycho Brahe in 1584. And he noticed that there was a change in the motion, change in the position, of Arcturus. The proper motion of Arcturus is about 2 arc seconds per year, so it's 5 times less than Barnard's star. And that's still really, really high, and it's reflective of a motion through space of about 120 kilometers per second. And that sort of velocity is something that I think non-astronomers sometimes struggle to deal with. All of the numbers we have in astrophysics are much, much higher than you'd be familiar with in other sciences. 120 kilometers every second. And that seems high, but that's half the speed that the sun is moving around the center of the galaxy, which is about 230 kilometers per second. So stars can often be moving quite fast, though when they're moving relative to each other, they're typically a bit low at about 20 kilometers per second. And these high speeds may seem high, but the distances away that these stars are makes measuring their proper motion very difficult. And that's because space is big. And so I'd like to turn to one of my favorite books now and share a quote with you. And this book says, "Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. You may think it's a long way down the road to the chemist, but that's just peanuts to space." Does anybody recognize that quote? A few hands in the air. Edward, you're nodding. Good, because we've read this book together. This is from The Hitchhiker's Guide to the Galaxy, which I'd encourage anybody with any passing interest in science to read, because it's not only very short, it's only about 100 pages, but it's a wonderful piece of science fiction and very entertaining to write. And even though there's political commentary in there, it holds up reasonably well for its age. Now, to give you an idea of some of the sizes of things in the universe, I thought we'd play the order of magnitude game. So what I've done here is I've put a scale bar, and I've gone from a scale of 10 to the 0 meters, that's 1 meter, that's something we're all familiar with, up to 10 to the 22 meters. And I've chosen 10 to the 22 meters because that is the distance to the most distant thing you can see. We'll come to that in a moment. So I'd like you to imagine something that's 10 to the 0 meters, or 1 meter. I've chosen my daughter Penelope. She's not always an angel. She's asleep at the moment, so she's pretty angelic. But 10 to the 0, or 1 meter, that's the typical scale of people within a factor of 2. Go up an order of magnitude, we've got the largest animals, the whales, at about 10 meters in length. And we go up to 100 meters, and we've got things like football pitches. Again, go up an order of magnitude, the Burj Khalifa, it's about 1,000 meters. And another order of magnitude, and we're at the scale of the highest point on Earth, Everest, which is about 10,000 meters. So we've immediately now gone 4 orders of magnitude from our scale of people up to the scale of the biggest things on Earth. But we can keep going, 10 to the 5 meters, and we're at small countries, that's the width of Israel. Or 10 to the 6 meters, or 1,000 kilometers, that's pretty much the length of the United Kingdom. So now we've gone 6 orders of magnitude. We're struggling to fully visualize, I think, how big 1,000 kilometers are. Unless you've probably walked it, and there's probably only one person in this room, I'd guess, who might have walked that, Rob, you probably can't imagine what 1,000 kilometers is like. You go up another order of magnitude, and you're at the size of the whole Earth, which is 10 to the 7 meters in diameter. Again, many of us will struggle to appreciate just how big the Earth is. We're sitting on a giant spherical rock in space, but most of us see the Earth around us as flat, and visualizing that can be sometimes difficult. Go up another order of magnitude to Saturn, the second largest planet in the solar system, and then another order of magnitude to the size of the Sun, 10 to the 9 meters, 100 times larger than the Earth. And people struggle sometimes with just how big the Sun is compared to the Earth because it's so distant. I'm including this picture of the Sun and the Earth because the Earth is on this picture. Can you see it? Yeah. There's the Earth, and everything I've concluded previously, everything on the Earth is within those few pixels there compared to the size of the Sun. But the Sun isn't even the biggest star. In fact, it's probably a little bit small. This is Pollux, one of the 2 stars of the Gemini constellation, which is about 10 times larger than the Sun. This is Rigel, the blue supergiant in Orion, which is about 100 times larger than the Sun. And that's about the size of the distance between the Earth and the Sun. So there's a star here so big that if you plopped it down in the center of our solar system, would almost envelop the Earth. But still, there are bigger stars. This is Betelgeuse. It's 1,000 times larger than the Sun. So large that it's actually partly resolved in some images. That's an actual very poorly resolved image of Betelgeuse. That's also the scale, roughly, of the entire solar system. So there are stars out there which, if you put them down in the middle of the solar system, would envelop all the planets. This is all the planets out to Pluto, which I'll include as a dwarf planet, is about the same size as Betelgeuse. But we can keep going a little bit further, and we get to the furthest man-made object, the Voyager spacecraft, which traveled to the outer planets in the solar system, and then just has kept on going, and it's currently traveling away from our sun at a rapid speed. Another order of magnitude, there's nothing really at 10 to the 14 meters that I thought would be relatable to you, or at 10 to the 15 meters, but at 10 to the 16 meters, you've got the typical distance between stars, and the distance, roughly, to the nearest star, Proxima Centauri, which is too faint for most of us to see with the naked eye. But 10 to the 16 meters, 3 orders of magnitude larger than the solar system, is the typical size between stars. So when you imagine stars floating around in the galaxy, and you think how crowded it might look, 99.9% of the space between stars is pretty empty. The solar systems, of which there are many out there, are taking up a small fraction of that space. But that's just the nearest star, and you can't see that. If you're looking out into the night sky, you're seeing slightly more distant stars that are typically more luminous. And we actually have to go 2 orders of magnitude further away to a scale of 10 to the 18 meters if we want to be able to look at the distances to the typical stars in the night sky. So we've gone 18 orders of magnitude already. Again, we jump forward a few more to 10 to the 21 meters if we want the entire Milky Way. So if we want to be able to study everything within our galaxy, we need to be looking on scales of 10 to the 21 meters. And then that final step takes us to Andromeda, the most distant object that most of us will be able to see with our naked eye, the Andromeda galaxy, 10 to the 22 meters. So hopefully this has given you some idea of just how big things are in space and how large the distances are between some of the objects and how difficult it is to measure even those vast speeds for objects that are 10 to the 18 meters away. But that was the challenge that the European Space Agency set itself in the 1960s when it designed the Hipparcos satellite, an astrometric mission that was going to measure the positions of stars. Not just their current positions, but also their proper motions as they move across the sky, and their parallax motion. Now, parallax is something absolutely fantastic that we can do to measure the distances to stars. And for this, I'm going to need you all to hold up a finger in front of you and close one of your eyes and look to see what your finger is projected against in the background. And then swap your eyes, and you'll see that your finger has moved compared to the background it was projected against. And this is shown here on the scale of our solar system, where the Earth, as it goes round the sun, will see a foreground star shown in red in a different position on one side of the sun to the other relative to those background stars. And this is a geometric way that we can measure the distances to stars. The larger the parallax motion, the closer the star is to us. And there's a little video here from the European Space Agency showing what Hipparcos would have observed as it observes stars over the course of the year, and their parallax motion takes them in these little circles in space. Now, this has been exaggerated so that you can get a feel for it. But every single star is doing this to some extent or the other. So not only do you have to measure this, but you also have to then solve a solution that involves all of these objects moving in that same way at the same time. But it's not just that they've got a parallax motion. Like I said, they've also got a proper motion. So in addition to that spiral, they're also moving across the sky. And so they trace out these complex, almost helix-like structures as they move across the sky. And you can characterize this with only 5 parameters, but you need to do it for every single star that you're observing. And Hipparcos did this for about 100,000 stars, 100,000 of the brightest stars, and it allowed us to determine distances and proper motions to those stars. But that was only a very, very small fraction of our Milky Way. And so they were already going about designing the next satellite that would follow it, and that would be Gaia. And Gaia is a satellite that has pretty much covered most of my research career on star clusters. From 2013 to 2025, it measured the positions, and therefore the parallaxes and proper motions, of 1 billion stars in the night sky across our galaxy, and even in distant galaxies, in some of the nearby galaxies that surround our Milky Way. And it's kind of difficult for me to really give you an impression of how precise an instrument this is. But I was able to work out one statistic for this to give you an idea of how accurate Gaia is able to measure the velocity of something moving across the plane of the sky. If you were to position Gaia on the Earth and you were stood on the moon, Gaia would be able to measure how fast the hairs on your head were growing. It's an absolutely stunning instrument. And I've used Gaia data, as well as other data, for most of the last 10 to 15 years, studying star clusters. And I'm interested in star clusters because they're really important for lots of different areas of astrophysics. Stars pretty much form in groups or clusters of some sort. So the clustering of stars plays some role in shaping the star formation process. And understanding that clustering is really important. Not only do stars form in clusters, but they spend their childhood in clusters. For the first 5 to 10 million years of their life, they're typically still in their birth environment. And it's during that time that planetary systems are forming. And so the birth environment, that star cluster, is really important for understanding not just the formation of planetary systems, but how the environment might affect the planetary system in terms of the motions of the planets or the atmospheres that those planets have. And finally, star clusters are often some of the most distant objects we can observe because you can see them within the spiral arms of distant galaxies, and you can use them to characterize the star formation that's occurred in distant galaxies. You can trace out that spiral arm structure using star clusters, and they're really a powerful tool when you're looking at distant galaxies. And star clusters come in quite a different range of masses. Even in our own Milky Way, we get little star clusters like Rho-Ophiuchi, which have maybe 100 stars in them, up to big star clusters like NGC 3603 with maybe 20,000 stars in it. We also get them in different sizes. Sometimes they're really clustered, and we see them like a star cluster that we might recognize. Other times, they're much more substructured with multiple little groups. And then other times, they're really spread out. And yet all these systems are sort of similar in age, and we don't quite understand why that happens. But we do see star clusters over a wide range of ages. We see very, very young systems that have ages of a few million years, where star formation is just finishing, up to ages of 100 megayears or so. This is the Pleiades star cluster that you can see with the naked eye. And this is one of the oldest star clusters in our galaxy with an age of 2 or 3 billion years. And we know that star clusters survive for this long period of time, but not all of them do. And we don't fully understand exactly what causes some of them to be disrupted and some of them not. So I've studied a huge number of different star clusters over the last 10 to 15 years. Cygnus OB2 is one of the regions I've studied the most. I was able to put together proper motions before Gaia data was available to map out the spatial motions of stars in the cluster. We expected Cygnus OB2 to have been the remnant of an expanded star cluster. So we're expecting all the stars to be sort of moving away from the center. But instead, we found their motions were a lot more complex and substructured. I'm showing their motion as a line on the sky here, and I've color-coded it according to the direction the star is moving. So you can see there's groups of stars in the same area with the same sort of color, because they're moving in the same direction. And what you're not seeing is a radial expansion pattern. Instead, you're seeing this sort of substructured motion. I also went to study the nearby Scorpius-Centaurus OB association, which is one of the nearest groups of young stars to the sun. This is about 100 parsecs away, so 200 or 300 light years from us. It covers quite a large area of the sky, so we had to use Gaia data for this. But again, we looked at the substructure of these to try to identify an expansion pattern, and again, we couldn't find that consistent expansion pattern that would suggest expansion from a single cluster. Instead, there's this much more substructured appearance with potentially multiple groups. And this has been verified since then by numerous other studies that have looked at this, looked at these associations, particularly Scorpius-Centaurus, and have found that these groups not only show the same kinematic patterns as we found, but also have similar ages in their substructures too. I was fortunate to be able to study some of the most famous nebulae as well. This is the Rosette Nebula. This is one of our IFAS images that I put together. And we studied this cluster of stars in the center. I was working with a friend of mine, Chris, and we were looking at the motions of the massive stars in the center of the cluster. And we identified two objects, this one here and this one here, that were moving directly opposite each other away from the center of the cluster. And we could trace their motions back and identify that they must have originated, if they had been together at some point in the past, from a point around about here. And it's likely this was originally a binary system of two very, very massive stars, possibly a triple system, which then got disrupted, and the stars flew off apart from each other. And these are called runaway stars, and they're really, really interesting for studying the dynamics of star clusters such as this. That's work that my PhD student Juan and my postdoc Christina are continuing with today, because we can use this to understand the dynamics of systems like this. I've also had a considerable interest in using stellar spectroscopy. Stars have very, very different spectra, as you can see here for different types of stars and how different their spectra look. And this is really useful. You can use this to determine the surface temperature of stars. You can infer the mass of individual stars. You can estimate whether they might be in a binary system. But also, critically, you can determine that third axis of motion. The proper motion that we can measure from Gaia is only showing you the motion across the plane of the sky. It's in 2 dimensions. If we want that third axis, the radial velocity, we need spectroscopy. Spectroscopy is in some ways a little easier to get for individual stars than proper motions, but it's harder to get for large numbers of stars. One of the things that I was able to do at Keele when I came here to work with Rob is to use data from the Gaia ESO survey, which was a large spectroscopic survey of multiple clusters, and we put together a very, very large study that we published a couple of years ago, where we looked at 18 different clusters with spectra of tens of thousands of objects, of which many thousands were members of young stars in these clusters, and we were able to perform a very detailed comparative study. So instead of studying one cluster and coming to a conclusion about that, we studied multiple systems with exactly the same methodology and were able to make a comparative analysis. And one of the things we found was that pretty much all these young clusters were in the process of expanding in some way. It wasn't always that they were expanding in a nice radial expansion pattern, but they were all expanding and drifting apart from each other. And that was really, really useful because we didn't know how many of these systems were gravitationally bound or how many would get disrupted or fall apart. So that was very, very useful to verify. Continuing with that spectroscopic work, we've gotten involved in 2 very large spectroscopic surveys that are coming up. One is taking place in Chile with the VISTA telescope. It's located here. That's in the southern hemisphere. And in the northern hemisphere, there's another facility being built on the William Herschel telescope in the Canary Islands. Now, what these two telescopes have adopted is a type of system called multi-object spectroscopy, where instead of taking a spectrum of a single object, you take spectrum of multiple stars at the same time. You position a series of optical fibers on the focal plane, and they use that to capture the light from individual stars, and that gets fed down into a spectrograph. And these have been in development in astronomy for many, many decades, and they've typically had tens or hundreds of fibers. But we're about to see two facilities come online that have, in the case of Weave, 1,000 fibers, and in the case of Foremost, in the southern hemisphere, 2,400 fibers. So in an hour of pointing at the sky, you could get a spectrum of 1,000 stars or 2,500 stars in one go. So this is going to turn stellar spectroscopy from something that was existing on small to medium scales for maybe hundreds of stars in a cluster to getting thousands or tens of thousands of stars in a cluster. And that will really, really revolutionize, I think, our kinematic studies of these clusters. And that's something I'm looking forward to working on in the next 5 or 10 years. For my final slide, I just want to thank you all for coming. I want to thank you all for being friends and family and supporting me in my journey here. I want to particularly thank my mum and dad. I want to thank my wife, Elizabeth, my children, Edward, Anne, Penelope, and Dylan. I want to thank my best friend, Christian. I want to thank my supervisors, Mike, Jeremy, Janet, and Rob. I want to thank my PhD students and postdocs, Joe, Sarah, Alexi, Becky, Juan, and Christina. I wasn't able to get a picture of the other Joe, sorry. And also I want to thank people at Keele who've been really supportive of my career over the last 10 years and have offered me advice and opportunities that I'm really grateful for. So thank you all very much.